everybody. So today we will be doing a live code of Lab 12, which is getting started with Project 3. We will be creating a hexagonal world, a world consisting of hexagons. And so this live code is a little bit different than normal live codes. Instead of doing it live in lab, we're going to do kind of a full live code right here, completely from the ground up, no matter how long it takes. That way you can kind of see the full process of doing something like this, and it won't be in the rushed setting of lab. So let's go ahead and get started. So what I will be working off of, I will be going completely off the starter code. The starter code for Lab 12 consists of HexWorld, which is just an empty class. It also has a boring world demo, which is a boring world. Well, might as well run it and see what it does. All it does is create a bunch of nothing and some wall tiles. So that's pretty boring. It just creates a square. And you can see that that kind of takes place in this loop. So first we fill the entire world with nothing, then we fill in that kind of box with walls, and then we render the frame. So we also have a random world demo, and the random world demo shows how we can get randomness in our world. So first let's just run it and see what it does. Oh wow, okay, so that's pretty random. Let's focus our attention maybe in this top left area, and we see a flower, two walls, and nothing. And now let's change the seed. So if you'll recall from the spec, changing the seed should change our randomness. And if we run this again, we should get something different. See, before we had a flower, two walls, and nothing, and now it's different. But if we go back to the original seed, we should have it the same again. And there we go, flower, two walls, and nothing. Awesome. And so how does this function work? Sorry, this class work? We have this fill with random tiles method. It loops through the entire board, and at each point it picks a random tile right here. So we'll work off of this this starter code because it's closer to what we want in HexWorld. In HexWorld we'll have to implement randomness. So we'll go ahead and just start from here. Let's copy and paste this code into HexWorld. Okay, great, we got this code. Let's just quickly do a hello world test and make sure our hex world actually runs. Right now, hex world should be a perfectly random world, and it is. Our copy paste worked just fine. But we really don't, at this moment, we don't really want a perfectly random world. We want to build a hexagonal world. So what I'm going to do is I'm going to get rid of this, random tile method, and instead of filling with random tiles, we're going to fill it with nothing tiles. We're going to create a blank canvas for ourselves. Okay, and then we'll call this like fill board with. Okay, so this will fill the board with nothing, and we can start off with that, and you should see that we have a blank world now. That is good, right? It's closer to what we want. We gotta have a blank world to have a hexagonal world. So, where to begin? There are a lot of places we can start, but I want to draw your attention to the spec. So let's go down to what do we want to build? We want to build a hexagonal world, right? The way it currently is written, is going to be too challenging to do in like a double for loop. One possibility is we could like loop over all of this regions, and at each location we could determine the correct tile to put there. If you tried it that way, that's a very good first approach. That's probably the most natural way to think about the task at the beginning, but it sounds really hard, and I don't want to do it that way because that sounds very challenging. So we can try to find a better way, a more clean way to do this. And a sort of natural way to break down this problem is into two steps, as the spec indicates, right? We can break it down into building a hexagon, just drawing a hexagon somewhere, and then tessellating the hexagons in this nice pattern and picking a random tile for each of the hexagons. So what we will do first is we will build hexagons first. Now, building a hexagon itself is not a straightforward task, right? Like, how do you build a hexagon of arbitrary size? See, this is a hexagon of size 3, we got 3 on the top, 3 on the sides, and, our kind of middle side has to always be of side length 2. This will make for nice tessellation. But this is a size 3 hexagon. We should be able to make size 4 hexagons, size 5 hexagons, and size 6 hexagons. So again, one solution, and a perfectly valid one at that, is to start at this tile, which is, you can't really see, it's a nothing tile right now, so it blends in with all the other tiles, but there's a unique tile here. We could iterate over all the rows and all the columns in this kind of way, and we could determine, okay, so here we're not going to do anything, here not do anything. Okay, here put I guess that's a tree or spade or whatever. Here put a tree, here put a tree, nothing, 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 tree, 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 nothing, etc., etc. Hopefully you get that as idea. But again, to me that sounds a little bit more challenging. So what I want to kind of do here is whenever we're faced with a difficult coding problem, the best thing to do is to take a step back, look at the whiteboard, and see what are some observations I can make about the problem at hand, and how can those observations help me come up with a cleaner solution. So the first observation I'll make, and this is after a series of iterations, but I'll save you all that. And the key observation here is that here on the first row, we see that the first row of the hexagon, don't touch it, tree, 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 don't touch it, is the same as the last row of the hexagon. Don't touch it, tree, 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 don't touch it. And we have that pattern repeat. The second row is the same as the second to last row. The third row is the same as the third to last row, right? So one kind of strategy we can take a look at here is recursion. So we can draw a row, so say the first row, so we draw the first row, then we can draw the remaining rows, and then simply draw the first row again, down here. And that is a valid recursive solution that will actually make our lives much easier. So to kind of demonstrate the validity of this approach, I am going to live code it in Python, because Python is nice and easy to understand, and we will use what we know well, which are print statements, and from there we'll get print statements instead of a tile rendering engine, and from there we'll get a working solution, and we'll map that solution back onto HexWorld. So I think this is definitely one way to work about a problem. Start on the whiteboard, or start in an easier language that you know well, right, like Python, and then we can move on to something harder. So I'm going to go to my desktop, and I'm going to vim hex.py. Okay, so here is just some boilerplate Python. This is not actually important. We're not learning Python in this class. This is just so it can accept command line arguments. Okay, so now our Python program can accept command line arguments, and we call draw hex on a hexagon of size s. Okay, I will call it n. We'll call it n. Okay, so a hexagon of size n, so you see here would be a size 3 hexagon. How do we draw this hexagon? So let's define a recursive helper function. Draw row, like a draw row, or actually, draw hex helper, we'll just call it like that. So what is some data that we need to keep track of? So it might be nice to keep track of n, just so we know. But the way we can approach this is how many, blank tiles do we have to put? And then how many real tiles do we have to put? And we'll kind of anchor our focus around this point, this top left point of the hexagon. And so for the first row, we need to put 2 blanks and 3 tiles. On the second row, we need to put 1 blank and 5 tiles. So you might see on the first time, you see the number of spaces decreases each time. And let's actually go to a bigger example to see this. Let's go to a 4x4. Yeah, so on the first row, we have to put, I believe, 3 spaces and 4 tiles. Okay, so it's 3 and 4. The number of spaces decreases by 1, and the number of tiles increases by 2, right? 1 here and 1 here. So it goes from 3, 4 to 2, 6 to 1, 8 to 0, 10. So that's one thing we'll keep in mind. And so one way to do this is to just define parameters. How many blanks do I have and how many tiles do I have on this current row? And maybe this will be sufficient, maybe it won't, we'll find out. So how do we do this? So in Python, I'm going to use print statements, which we know and love, and later we're going to map this onto Java. So the first thing I want to do is print B spaces, how many blanks do I have? And then I want to print tiles. Well, I'll just call my tiles X here. It doesn't actually matter. How many tiles do I want to print? I want to print T of them. Nice. And so that's how I print the first row of the hexagon. And remember what we said, print row 1, print last, or it's really, print this row, print this row's reflection. So like by reflection, I mean for row 1, its reflection is this last row. For row 2, its reflection is this row, etc., etc. And from what we talked about before, it's print a row, print the remaining rows recursively, and print the same row again. Once we print, and then that's the hexagon. So what is the recursive call? So in the recursive call, if some base case, if some condition, we don't always want to infinitely recurse. You want to stop recursing at some point. But if I haven't figured out the condition yet. But what do we want to do? We want to draw a hex helper. We keep n the same. N is just a parameter. We haven't actually used it yet. We may never use it, and in which case we can take it out. But we'll want to draw a hex helper. N, which is the same total, size of the hexagon. In this case, it's 4. It'll always be 4 throughout this size 4 hexagon. How many blank spaces do we need? Well, we need, 1 less blank space. So we go from 4 to 3 to 2, 3 to 2 to 1 to 0. And how many tiles do we need to draw? We need to draw 2 extra tiles. Okay, and now this is a good start because then we see that we want to stop recursing when we hit 0 blank tiles. So like, we were starting at this anchor point. Here it's 0 blank tiles and we start immediately printing tiles. So if, B is greater than 0, then we want to recurse, because if it is 0, we're done recursing. We don't want to recurse. This row is printed, no recursion, and we print its reflection. So, print the rest. So that's it. Finally, we need to just call our helper function. We'll call, draw hex, n. We never actually used n, so let's just go ahead and get rid of it. We might have to bring it back. I don't quite know yet, but for now, let's just get rid of it. We were only using b and t. Okay, so we'll draw hex, and how many blank spaces do we have in the beginning? Well, it appears that we have 1, 2, 3, and this is of size 4, so n is 4, and this generalizes, so we have n minus 1 blank spaces and n tiles in the very first row. And so this should be sufficient. Let's try it out and see if it works. So let's go python 3 hex.py3. Uh-oh. Draw hex takes in 1 positional argument. That makes sense. I probably, yep. I meant to call draw hex helper here. Okay, awesome. This looks very good. This is the exact, this is what we want. Let's just show you so we can compare. You see there's 3 on the top, then the next row has 5, then the next row has 7. That repeats twice, and then we repeat down. Let's try a line 4 hexagon. Great, so it's 4, 6, 8, 10, and then repeat backwards down. So this looks good. Let's try a larger hexagon, maybe 6. Very good. And remember, it's important to remember that our middle row is always 2, and this was dictated by the spec. So great. We've taken a very complicated problem in drawing a hexagon, and we reasoned about it mathematically. We figured out a nice observation, and the observation is that this reflective pattern of the hexagon, where this top half is sort of reflects onto the bottom half, that can be handled very nicely with the recursive calls. So cool. But our job was not to print x's in Python. Our job was to draw tiles in Java. So let us let's keep our code open, and we will reference it as we're doing Java. But so what's the kind of the first thing we need to do? So what are some primitives we take advantage of in Python? So the main primitive we take advantage of is this print statement. If we have an analogous print statement, and I say that in air quotes, in our tile rendering engine, I think we'll be in good shape. Because we can call functions in Java, we can recurse in Java, and that's pretty much it. So as long as we have a way to, print out a single row, really, that's what this represents, to kind of draw a single row, we're good. So the other kind of primitive that we're missing is in Python, we always start in the same location, right? We're starting at the top left. But we may not always want that for HexWorld. So you might recall for HexWorld, we can start our tessellation here and start tessellating here. We can start a tessellation here and here. Basically, we want a sort of anchor point for the tessellation. And in Python, that anchor point is like 0, 0, this square right here. That's the anchor point. But we might want to start anchoring the tessellations from like right here. So where I'm getting at is we need a better way. In Python we didn't need to deal with this, but in our HexWorld we'll absolutely need to deal with sort of your location. And I think the Boring World demo is a really good example of this. So let me just run that real quick. So in the Boring World demo, our anchor was sort of this tile right here. That's where we anchored our square. But equivalently, we could anchor this rectangle, over here and draw it over here. In fact, let's try that out just so you sort of get where I'm coming from. So let's go to Boring World. You see we start at 25, but we can also start at maybe 2020 and see what happens here. Oops, I made a bug. 20 and IntelliJ caught me. This is always false. And so let's go from 20 to 25. So you see we kind of anchored our rectangle, at a higher location. And the bug I just committed is a really great reason to see that we really need a better way of dealing with positions than using coordinates just randomly interspersed throughout our code. So one way we can do this is we can literally formalize a position private helper class. So private class position. And we don't need to make this a fancy class. It can just have an int x and an int y. It can have a constructor position int x int y, and it can do this dot x is x, this dot y is y. And later we might add to this. We might, but for now this is okay. Okay, great. So we have a way to deal with positions. Now we can use those positions to draw a row to the board anchored at a given, draw a row of tiles to the board anchored at a given position. Nice. So what do we want? We want a method that's public void draw row. We want to draw a row, and what's it going to take in? Well, it's going to take in a position p. That's going to be our anchor point. It's going to take in a tile that we want to draw. What else would we need? We need a position, a tile, and we probably need the actual tile array. So tiles. That sounds good, like a good start to me. And what we can simply do is we can just say for int x equals p dot x, x, oh, well, we also need to, tell how int length. We need to see how long we need to draw the row. Well, we can actually do it like this. Let's go from 0 to length. Let's call it dx. I want to call it dx. Well, dx is less than length, dx plus plus. Now we can do tiles of p dot x plus dx, p dot y equals tile. That should suffice for drawing a row to the board. Why is this? Well, we start at, when dx is 0, this is just tile px, py. So at position, which represents an x and a y, we draw the tile. And then we increment, we go 1 to the right by setting dx to 1. And then 1 to the right, and 1 to the right, and 1 to the right. And each of those times we fill the desired tile into the tiles array. So let's sanity check and make sure that this actually works. So we can fill the board with nothing. And I also just want to, I don't want to play around in main method too much. I want to finalize our main method. So we're actually going to use a separate method real quick. Draws the hexagonal world. Public static void draw world. And what does it need? It just really needs the tile array. And right now what we want to do is, I don't want to call this random tiles. That was a legacy of the random, the random world demo, but really we'll just call this world. That's a better word for it. So instead of filling the board with nothing, we'll call draw world tiles, draw world. And then, now in here, when we're done, this is going to be the place where we draw the tessellation and, make it correct. But for now, we're going to use this as a play area. And it's nice to have like a separate play area than our main method, because I don't want to accidentally introduce a bug into the main method that I forget how to fix. So for now, we're just going to fill the board with nothing. And then let's try drawing a row. So let's draw a row. And what do we need? We need tiles, a position, a tile, and a length. So real quick, let's create a new position. So position P equals new position. We'll do 2020 like we had in the previous. BYOW world. Hex that this cannot be referenced from a static context, because this should be a static class. We created a non-static class, which is, we're doing everything static here, so we need to have a static class. I won't go into too much of that, because that's kind of like week 1 Java type thing. So let's move on. So we need a static class, and now we finally have a position. And then what do we do here? We want to draw a row with the tiles array. And what other parameters do we need? Position, a tile, and a length. So we'll use P as our position. We'll do tileset.water for our tile, and length is 10. So let's see if this works. And we want to run HexWorld. So let's run hexworld.main. Okay, indeed it seems it works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 water tiles were drawn. So I feel good about our draw row method. Now we have our primitives to draw a hexagon. So let's draw the hexagon. Let's remind ourselves of the code. The code is this. So we'll need a draw hex method and a draw hex helper method. So let's go ahead and do this. I believe we were supposed to call the draw hex method add hexagon. So let's do this. Public static void add hexagon. It'll probably need the tile array, and it'll probably need the size of the hexagon. Oh, and we also need a position to anchor the hexagon. As a hexagon to the world at position P of size. Okay. So first we hexagons are not valid if size is less than 2, so if size is less than or equal to 2, we'll do 3. Can we do a 2 size hexagon? Does that make sense? Let's find out. 2 size hexagon. I guess that makes sense. So we'll do if size is less than 2, return. Let's just not do anything. Now, if size is greater than 2, we might throw an exception or something. If we want really robust industry level code, we could throw an exception here and say, hey, that's not valid. I don't really want to go into that because we're going to be able to control exactly the size of the hexagon, and we're going to hard code it into HexWorld. And so we'll just make sure we don't pass in something less than 2. But then we'll call our recursive helper method. So we'll call this, we'll define, let's go. Okay, so let's go public static void. We'll go add hexagon helper just as we had before. It'll still need all these things, except it will need a number of blank spaces and the number of tiles, and also as above we need the specific tile that we want. Okay, and where did I get this B and T from? That's the same as we had in Python, but all these extra things, the tile array, the position, and the actual tile, we'll need that because we're using the tile rendering engine. Okay, so let's map our code into Java, and I'm going to do that by just copying and pasting the code into a comment. That way we can see it. So the first thing we want to do is print the first row. Now, it's printing spaces in Python is not the same as what we want to do here. Oops. Did not want to do that. Hopefully nothing was there. So what do we want to print here? Well, we want to print, instead of printing literal spaces, we just want to not touch these tiles. That allows us to do our tessellation, right? If we're drawing this green hexagon right here, and for we print actual spaces here, or we actually draw tileset.nothing here, or we actually draw tileset.nothing here, it's going to be challenging to tessellate because if I draw tileset.nothing here, it's going to overwrite this hexagon in these squares with tileset.nothing, and I don't actually want that. So instead of writing tileset.nothing here, I just want to not write anything there. So how can I do that? Well, instead of printing B spaces, what we can do is we can shift this position over B units to the right. And if we shift that unit, if we shift it over B units to the right, and then only draw the tiles, that will suffice as drawing nothing, right? And how do we draw the tiles? We do it with draw row. So what will that look like? Well, we'll have to have a way that we can shift a position over by an amount. So let's put that into our position class. So our position class can has another method, maybe public void. It can have public void shift, or really not void shift. We want it to return a new position shift, and we shift by int dx, int dy, and it can return a new position, this dot x plus dx, this dot y plus dy. So it's a way we can take a position and get a new position, dy. Thank you, IntelliJ. It's a way we can take the current position and get a new position from it, basically. And we can specify a relative distance in x and y. So position start of row is equal to p dot shift, and how we want to shift it over b in the x direction and 0 in the y direction. Now this shift is the same as the shift is like the analogy of printing spaces, except we kind of just, instead of printing tileset.nothing, we shift over. And now we're going to draw a tile. So how do we draw tiles? Well, we say draw row, and we pass in the tiles array. We pass in the start of row position because that's where we want to start drawing. we want to draw with the given tile that we're given in add hexagon, because the hexagon's all going to have the same type of tile. And how far do we want to draw? We want to draw T. Okay, and now remember what I said from earlier. There is like an inherent recursion, right, with this. So we can simply, you know, draw this row, draw remaining rows recursively, and then we can draw this row again to be the reflection. And this is an analog of this code right here, print this row's reflection. So what I can't do is just literally copy this, right? If I just copy this, what you'll find is that I'm just literally drawing to the exact same location, because start of row is a position, right? So if I just copy this line, I'll just draw these tiles T times right over this draw row. It'll be the exact same location. In Python, when I did the same print statement, it ended up in different locations, but that's because of the way print works. You know, I printed this guy, and then I printed a bunch more stuff, and then when I print again, I print below it. You know, every print reduces the row, right? We don't have that here. Our draw row doesn't reduce the row, or like go down one row every single time. Maybe a valid design choice would be to have draw row go down every single time, maybe with the class variable, like, you know, draw row print line or something. But that's not what we want to do here. I think that's a slightly more complicated than we need. Instead, what we need to do is we need to create a new position, start of reflected row. And that's going to be some sort of shift from start of row. You know, what is the shift going to be? Let's find out. So if I have, let's go to the normal 3x3 example. If I draw this row has the same x coordinate as its reflection. So we know we don't have to shift any in the x direction. We just have to shift downwards some amount in the y direction. So how much down do we have to shift? Well, on a 3x3, we see we have to shift down 1, 2, 3, 4, 5. Okay, interesting. You know, it goes from 3 to 5. What about on a 4x4? Sorry, not a 4x4, but a size 4 hexagon. Well, we have to go down 1, 2, 3, 4, 5, 6, 7. So it seems that the function that we want here is 2n minus 1, right? When n is 4, we have to go down 7. 2 times 4 is 8, minus 1 is 7. When n is 3, we had to go down 5. 2 times 3 minus 1 is 5. And that makes sense, because we're just, the sides of the hexagon, like this expanding region of the hexagon is size n. This expanding region of the hexagon is size n. And we're already on the first row, so we have to go down 2n and then back up 1. So 2n minus 1. Okay, so the start of the reflected row is going to be 2 times n minus 1. And see, this is where our Java implementation is going to slightly differ from our Python implementation. Remember, in the Python implementation, I actually just instinctively put the variable n in our parameter list here because I thought it might be helpful. Turned out in the Python implementation it was not helpful, but here in the Java implementation it's indeed helpful, so let's keep it around. So now we have a start of a reflected row, and we want to start drawing the tiles there. So I think this is a really good place to pause. You know, before we do complicated recursion, let's just make sure we have drawn things correctly. So I want to call this add hexagon helper function in our play world. So let's actually go over here. Instead of drawing a single row, let's call add hexagon helper, and we'll call it on tiles. We'll call it at this position P we defined. We'll use a tile set dot, what should we do? Let's go flower. Let's do a size 3 hexagon. And B and T we'll have to specify. So for now, remember, B is the number of blank spaces, T is the number of tiles. So for now, we'll just specify them as 3 and 3. When we draw, like our recursive helper function, we'll eventually have to get rid of these parameters by having a wrapper function, but we'll get to that later. For now, let's just call them. Let's just define them as 3. And let's run our world and see if we did anything egregiously messed up. Nope, this looks good. So there seems to be space for 1, 2, 3, 4. I'm just guessing. So it seems for where we are right now, we're doing fine. Okay, so now let's draw our remaining rows recursively, and let's again look at our Python and see how we did this. So our Python said, if b is greater than 0, we want to add hexagon helper tiles. We want to remember, we actually want to decrease the row. So we want to decrease the pointer p. Why do we want to decrease p? Because first we're processing this row, then we want to process this row. So the p value for this row would actually be 1 down from the p value from this row. So in Python, again, this was taken care of by our print function, but it's not going to be taken care of here. So we have to do next p equals p dot shift, and we want to go 0 in the x direction and down 1. We just literally want to move down a single row. So instead of processing row 0, we start processing row 1 and then row 2. Okay, and so we want to pass in tiles to the recursive call. Next p to the recursive call, we want to draw the same tile. N is going to be the same, it's just the size of the hexagon. But remember, from our code here, the number of blank tiles goes down by 1, and the number of actual tiles that need to be drawn goes up by 2. Okay, I think we have used all the Python code, used what we need from there, so let's go ahead and actually just try HexWorld and see what happens. Oh man, okay, so this is fun. Because this is the first real bug that I've introduced, and I actually have no idea where I introduced it. So first, it's clear. I see where I've introduced it. Okay, so I know I didn't articulate that thought process too well out loud, but I'll take a step back and do it. So if you'll recall, what we had in our original test, when this code is commented out, I'll just go there again, run it again. What we had is this kind of separation. So we went down a certain amount from this hexagon. Sorry, not this hexagon. This initial row, we went down a certain amount and drew it. Now, for the next row, here we went down, it seems 1, 2, 3, 4, 5. For the next row, we need to only go down 1, 2, 3. But it seems the bug here is that we went down 5 for every row. So we drew, oops, I forgot to uncomment the code. Let's uncomment this and see what happens. Let's run it again. So the bug here is it seems I went down 1, 2, 3, 4, 5 for the first tile, but also for the first row, but also 1, 2, 3, 4, 5 for the second row, etc., etc. So that's the bug. We don't want the bug is on this line, 46. We don't want the start of the row to always be 2 times n minus 1. Really what we want the start to be, oops, I keep going to that. Really what we want to start, it's 2n minus 1 on the first time, but on the second time, it's that minus 2. So really we can try to come up with a formulation mathematically based on the number of blank spaces. Oops. So when there is 1, 2 blank spaces, it's 5. When there's 1 blank space, it is 1, 2, 3. And when there's 0 blank spaces, it's 1. So it appears that we can actually calculate it as negative 2b plus 1. How did I come up with that? Well, first let's see if it works, and then I'll explain if it works. Otherwise, we'll go back to the drawing board. Yes, okay, there it is. So it looks a little bit off the hexagon actually, but we'll come back to that in a second. How did I get this? Well, so when there's 2 blank tiles on the first row, we need to go down 1, 2, 3, 4, 5. When there's 1 blank tile, we need to go down 1, 2, 3. So I'm already seeing a pattern. 2 makes 5, 1 makes 3. It seems to be the number of blank tiles times 2 plus 1, and that works for all of them. Okay, so now let's see why our world looks a little bit weird. 1, 2, 3, 4, 5, 6, 7. Oh, I went down too far. How is that? And it appears what it wants me to do is this, but not actually sure why that makes sense. Let's try this out. Oh, no, that doesn't work. 2b plus 1 makes sense. So I'm wondering... Oh, okay. I was wondering why our size 3 hexagon looks different than this size 3 hexagon. But I doubted my calculation, but I don't think my calculation is wrong. What's really wrong is the way we passed in parameters. So let's not worry about that for now. And instead, let's just move on to finishing the hexagon. And I'm pretty sure the problem will resolve itself. And if it doesn't, we'll again return to the drawing board. Okay, so we've successfully drawn add hexagon helper. So now how do we do add hexagon? Well, it's the same as the Python code, which says we just need to call it on n-1 and n, where n-1 is b and n is t. And that's actually the bug here because I called it on 3, the same value here, but it should have been 2. Actually, let's just see if that works. Yeah, there you go. There's the right hexagon. Okay, awesome. So now we just initialize this, so we'll call this add hexagon helper tiles. We want to anchor the first row at the same anchor point of the entire hexagon. What tile do we need to use? Well, someone should pass that into this function. I don't want to worry about what tile I need to use in add hexagon. Someone else can tell me that. The value of n, by the way, funny enough, we actually didn't use n again, so made the same mistake twice. Let's take out n and n from here. Okay, so we don't need n, we do need b, which is going to be size minus 1. Here it was, size minus 1 and then size. Okay, so we now have an add hexagon function. So let's just make sure our add hexagon function works. Let's get rid of this line. Add hexagon, and it takes in tiles, and I already forget what it takes in. Position, tile, and size. P tile dot tile, tile set dot, which one should we use? Avatar sounds pretty cool. And size can be 3. Let's try this out. And nice, we have a size 3 of avatars. Let's also try size 4 just to make sure we're not, it didn't make a bug by only testing with one size. And great, this looks like the correct size 4 hexagon. Awesome. So we're doing really good. We have, in not that many lines of code, drawn hexagons. So what is the next challenge? The next challenge is that, one, we need to be able to randomly we need to draw hexagons of random biomes. So I'm going to revert to random world demo, and we're going to be able to pick a random tile again. I'm just going to copy this code. Okay, let us paste this code, and let's go to tile set and let's figure out all the stuff we want. So I don't want an avatar. That's not a biome, not a wall, not a floor, not a nothing. Grass is we'll get grass. Just remember this over here somewhere. Water is not really biome. This is supposed to be Settlers of Catan, so it's on water. Sorry, it's not on water. It's on land. Not a locked door, not an unlocked door. Sand, mountain, and tree. Sand, mountain, tree. Okay, so let's see. Let's replace this with grass, flower, sand. Let's go case 3, return tile set dot mountain. Case 4, return tile set dot tree. So there we go. We have what we want, and let's choose a random number between 0 and 4 this time. I believe that's what random.nextInt does. It's what it usually does. I'm just going to take it on faith that we never get tileset.nothing. Now that will pick a random tile. So let's see if this works. Let's actually call. Oops, had an alarm go off. Sorry about that, but let's actually call this, instead of hard coding tileset.avatar, let's, hard code, and, let's get a random tile in there. And let's see if this works. Okay, good, we got mountains this time, nice. If we change the seed, we should get a different something that's not mountains. Grass, okay, nice. Cool. So we've now solved another problem. So we now can get a hexagon of random color, biome, or whatever, right? The last problem is to draw this nice tessellation of hexagons. And so the way I'd like to break down this problem is to break it down in terms of columns of hexagons. So you'll see that this is actually composed of 1, 2, 3, 4, 5 columns of hexagons. So we first will just try to build a random column of hexagons, and by random, I mean a column of hexagons where each of the biomes is chosen randomly. And then we can use that building a column of hexagons to build the entire thing. So let us take that idea and run with it. So let's create a function that adds a column of hexagons, each of whose biomes are chosen randomly, to the world at position P. Each of the hexagons are of size. I'm getting a little lazy with my commenting, but hopefully you guys don't mind too much. And let's copy some parameters. They'll probably come in handy. Okay, what we don't need is this because we'll randomly be picking the tiles. And I think this should be good in terms of columns. Now, what do? That's a good question. So before we jump into code, really, how would we, draw a hex column? So this is an interesting problem, but notice that this problem too has a recursive element to it. Drawing a column of, say, size 3 is the same as drawing a hexagon and drawing a column of size 2 below it, right? So we can also frame this recursively. And so the only thing we'll need that's not super trivial is I'm given the position P right here. So I can draw a hexagon at this position easily. I just pass in P, right? But when I need to recursively call this function, I need to call it on this kind of P prime down here. So how do I go from P to P prime? Well, let's actually abstract that into a helper function. So, a positional helper function. So let's get the bottom neighbor of a hexagon at position P. Gets the position of the bottom neighbor of a hexagon at position P. Okay, nice. So how do we, now we have to do some math again, and math isn't fun, but you'll see that if we have a hexagon of size 3, we just need to go down 6, right? It's really just, we go down 1, 2, 3, 4, 5, 6. So it's really just 2 times less, and I'm pretty sure that holds for everything. Let's try it over here. If I want the bottom neighbor of this guy, go down 4, right? This is size 2. 1, 2, 3, 4. This is indeed the guy. And you might notice I'm counting based on, this tile, even though the position really is here. Oops. Even though the position really is here, it's hard to count through nothing tiles. So I'm just kind of like shifting everything over to the right so I have a frame of reference. So I'm pretty sure this should be just return p.shift. We don't want to go anywhere in the x direction, but we do want to go -2 times size. Really, we'll go n, in the y direction. And so we should also take an int n here. N is the size of the hexagons we are tessellating. I hope that's how you spell tessellating. I think IntelliJ has a spell checker. Yes, IntelliJ has a spell checker, so that's good. Awesome. So now we have a get bottom neighbor function, and so with add hex column recursively, add hexagon, and the get bottom neighbor, I think we're in good shape to go ahead and write this function. So if size is, if size is less than 1, just return, forget about it. But let's ignore that case, and if size if size is greater than 1, we want to recurse, but before we do that, we draw this hexagon, draw n-1 hexagons below it. Okay, how do we draw this hexagon? Let's just add a hexagon at this location, add it to tiles at position P with a random tile. So how do we get a random tile? We can just call this random tile function, random tile. Actually, I really want to call this random biome because it's really a random biome, right? It's not a perfectly random tile. Let's go to see where did we use random tile. Let's fix those. Okay, oops. Random tile. Okay, it doesn't seem we used it anywhere else. Okay, great. So I want to use a random biome, and the hexagons are all going to be of the same size. Now finally, if size is greater than 1, I want to add a hex column. Or, well, really we want to say position bottom neighbor equals get bottom neighbor of position P with n as the size. So now we draw to the tiles a hex column anchored at position bottom neighbor, and all the hexagons are still the same size. So I think that should do it. Let's go ahead and try it out and see if we got somewhere. So instead of adding a hexagon to P, let's just add a hex column. And oops, I think I made a mistake. Yeah, I made a mistake. We also need to keep track of int num. How many are we adding to the column? Adds a column of num hexagons. So I don't know what I was thinking, but we also need to make sure we don't infinitely recurse. Okay, so let's review. If size is less than 1, or really not if size is less than 1, if num is less than 1. If we're trying to draw less than 1 hexagon, that's no good. So we'll draw this hexagon, and the hexagon is n tiles, P, random biome, and hexagon has a given size. That's very good. And then now, if num is greater than 1, we recurse. Get the bottom neighbor with size. Size is the size of the hexagon, so that's correct. Tiles, bottom neighbor, size of the hexagon, and n-1. Okay, so now I think this will work. So we add to tiles, and what is add hex column? I'll just copy this so I can write the signature easily. Okay, so we want to add to tiles at position P. We'll do size 3 hexagons, and we'll do 4 of them. Hopefully it doesn't draw off the edge of the world, but let's try running this and see if we were able to add a hex column. Uh-oh. Something went wrong. Index -1 out of bounds for length 50. Oh, I think this is honestly just, let's try drawing higher. I think we just drew off the edge of the world. So let's try anchoring this at position Y40. Yeah, okay, we did just draw off the edge of the world. What happened is we started like right here, and it tried to draw like into the negatives, and it was not happy with that. Okay, great. So we do have the ability to create a hex column. Nice. I'm pretty happy with that. And now we can try to see if we can use our column drawing abilities to create the final tessellation. So let's do it. So one thing you might notice about this problem is, now let's again, go back to this principle of stepping back to the whiteboard and saying, what kind of structure can we take from this? Mathematical structure can we take from this? And how can we use that to make our code easier? So you'll see that we draw a column of size 3, and then a column of size 4 slightly above it, and then a column of size 5 slightly above it, and then 4 and 3 again, right? So it's like for this, we can call this tessellation a tessellation of size 3. So, it's a tessellation of size 3, and each of the hexagons is also size 3, but you can vary that. So here would be a tessellation of size 3, but each of the hexagons is size 4. Cool. So for a tessellation of size 3, we draw a column of length size, and then we draw another column of size plus 1, and then we draw another column of size plus 2, and we do this kind of increasing size times, and we do this decreasing size minus 1 times. So why don't we just quite literally map that into a for loop? So let us pick. We'll overwrite draw world with now the tessellation code. So and I actually kind of want to move the fill board with nothing tiles out. Let's move it out because it makes sense to just, in our main method, initialize our stuff. Initialize our t tile array with tileset.nothing, so that way then we draw what we want and then we render it. So this, I think, is a nicer kind of abstraction. Okay, so how do we do this? We basically want some sort of for loop. So we want to draw world tiles. We also want to know what size, int hex size, int test size, like what tessellation size we want to draw. So where to begin? So basically we can go for int I equals 0, I is less than test size I plus plus, and this can be kind of expand up and to the right, and this can be expand down and to the right. Up and to the right, down and to the right. And you see and this time we only go for in I equals 0, I is less than test size minus 1. Okay, so this is going to be the basic structure of our code. And the first thing we want to do is we want to draw a hexagon at position P, right? Or draw a hexagon column at position P, and then we want to move up and to the right. So before we move on with this method, let's kind of characterize what moving up and to the right means. So if we want to get the position of a hexagon up and to the right, we need to go from this anchor point to this anchor point, or equivalently in terms of shifts, like from this point to this point. So let's calculate how many that is. We have to shift over for size 3, 1, 2, 3, 4, 5, so 2s minus 1, and then up 1, 2, 3. So let's map that into code. Yeah, okay. Draw world, and then we'll just start with 3, just get rid of that error. So just like we had this get bottom neighbor, let's define a position of the top right neighbor of a hexagon at position P, and it's the size of the hexagon on the right. Tessellating. And I really should have just copied and pasted it, but I'll start now. So let's get top right neighbor for position P. And what did we say? In X we go over 2 times n minus 1. And in Y we go up n. So up and to the right. And equivalently, we should probably also define a get bottom right neighbor. And so what is a bottom right neighbor? So let's see if we can get to there. So I basically want to go from here to here, right? I want to get the bottom right neighbor. So how many do I have to go down? 1, 2, 3 down. And how many do I have to go over? 1, 2, 3, 4, 5. So it's basically the same as get top right neighbor, except we have to go in the negative y direction instead of the positive y direction. Great, so now we've kind of formalized how to get bottom and top right neighbors. Now we can map this into code. So fundamentally what this is going to look like is we do something like, okay, we want to also anchor this at a position P. Fundamentally, this is going to look something like, P is equal to get top right neighbor P, and then we're going to draw a hex column there. And what's the hex column signature again? This is the hex column signature, so let's copy that. And by the way, this is, oh, and it also needs this hex size. And this is not correct code right now. We're just writing down thoughts. And then we're going to add hex column of tiles at position P, and size is the size of the hexagons. So let's do hex size, and num is the length of the column. So we want to do test size plus I, right? Because in the first case, we want to do, if this, we agreed the test size was 3, so first we want to do 3, then 3 plus 1, then 3 plus 2. So we'll do test size plus I. So this looks pretty good to me. What we do, oops, did I miss something? Tiles, position, no, I didn't miss anything. Okay, so here we have an off by 1 error, right? Because right now, the first thing we do is get the top right neighbor. So we start here, and then we move. That's not really ideal. So what we can do, if you add hex column and then get top right, add the column. Yeah, that'll throw us off. So what we can do is we can kind of, so the issue is the first thing we do is get the top right neighbor. So instead of drawing this row, we go up to the right and then draw the 3 and then draw the 4. So we can just kind of, draw the first hexagon and then expand up into the right. And so the expansion should start at 1. And then we do add hex column tiles P hex size test size. Okay, so what did I do here? So I just took out the first iteration of the for loop, and I just draw the first hex column, and then we start the expansion. So at I equals 1, we go up to the right, and then draw test plus 1, then up to the right and draw test plus 2. Now expanding down, we want to basically do the same thing. We want to say P is equal to get bottom right neighbor of P in hex size, and then we want to add hex column of tiles P hex size. And then now here's the tricky part. We do want to go down to the right, but how much down to the right? Let's see. So if we start at 0, what would be nice if we could just also do test size plus I. If we could do test size plus I, that would be nice, but currently that's not going to work because test size is 3, so this means that at this row I draw 3, and at this row I draw 4, which is not what I want. So maybe instead of looping forwards, we'll loop backwards. So we start at the last iteration of the loop, and the last iteration of the loop is when I is actually test size minus 2 because of this less than. So we'll start at test size minus 2, and we'll go until I is greater than or equal to 0. Does this make sense? So if we have a test size is 3, we start at 1 and we end at 0, which makes sense, yeah. So we want a delta of 1 and then a delta of 0. So this should work. To kind of, I just realized I said that pretty fast, and this is a little bit complicated, so I'll go through it one more time. So really what we want is, for test size 3, we want to first draw 4 and then draw 3 in the column. So test size is 3, so the first thing we want is I to be 1, then I to be 0. So that is accomplished by this loop. Why? Because when test size is 3, 3 minus 2 is 1, so we start at 1, and we only quit when I is 0. And this will scale up properly, right? If we look at a test size of 4 and stuff, it'll totally scale properly, because when it's 4, we then want it to be 3, 2, or when it's 4, when the test size is 4, it'll go 4, 5, 6. It'll go 4, 5, 6, 7, and then we want it to go 6, 5, 4. And so 6, 5, 4 should be mapped down to deltas of 210, and so 4 minus 210. Yeah. Okay, so that works. If that didn't make sense, just try to convince yourself of the math. It shouldn't be too difficult to convince, and maybe you can actually come up with a better way of doing it. But let's try. Oh, we have an error somewhere. Oh, we need to anchor it at a position P. So we added a position parameter here, so let's add a position parameter here. And we'll just say position anchor is new position 1234. And we just guessed it that way. We picked it arbitrarily, and then we started anchor. Okay, cool. Now let's see if we've done it. Uh-oh, we have not done it. And what happened? Index out of bounds. Index -1 out of bounds for length 50. So let's probably just increase this to maybe 45 and see if we did that. Uh-oh. Index 51 out of bounds for length 50. So let's try axis 1. Oh. Oh, I see what's happening. So let's try a hex size of like 2. See if we can get this down. This is probably one of the annoying parts, is we have to make sure our world fits in everywhere. Draw row. Yeah. Okay, so what's happening is that somehow we've our hexagons are going off the world. So let's just comment half the code out and see if we can see anything. Okay, so this is good. We can see something. So immediately I'm thinking we should move this down and to the right. Let's try like 30 and maybe 20. Let's go more to the left, I think. Maybe x is 10. Okay, nice. That looks good. So now let us try expanding up into the right and see what happens. Oh, this looks very good. This looks very good. Nice. That's exactly what we wanted. And let's try expanding down to the left. Maybe this is where we have the bug. Ah, okay, so this looks good. We have a bug here. Nice. Get bottom right neighbor p hex size. Interesting. Interesting, interesting, interesting. I wonder if we just try to do one of these iterations and see if we get a bug. So I'm just going to manually do one iteration of this loop. Oops, give me back. And we'll just do test size +1 because that's what we expect there. Oh, that looks good actually. That looks good. Let's increase the size to size 3. Just okay, that looks very good. So we have some sort of loop bug. Let's just try for sanity to do this again. So the second loop that we should be having, test size +0. Yeah, that's true. It can be replaced with test size. Okay, so our logic is working, but our for loop is not. So why is this? One thing we can try is to just print p get bottom right neighbor p hex size at column tiles p hex size test size +I. We can just try instead of actually doing this, let's just try to print test size +I. Make sure it's working. Oh, I can't do print I because it's not. Let's try running this again, and we should see print output actually. Oh yeah, this doesn't look good. You see, it's actually infinite looping. Okay, well, so it's probably because test size. Oh, there you go. You guys probably saw that for a long time and have been like worried about it, but it's because we were adding and not decrementing. Okay, Well, a bug found. So let us see if the bug, our code is good. See if now it's finally working. Okay, now it is finally working. So hopefully I didn't cause you guys too much pain with that bug, but now we are done. We have drawn a hexagon world. So let's play around with it for a couple seconds. Let's try increasing the test size. Let's move this a little bit. Let's try increasing the hex size to 4, but let's keep a tessellation of size 3. Nice, looks good, looks good. Let's try using a hex size of 3, but a tessellation of size 4. Maybe this will draw off the edge of the world. We'll find out. No, it did not draw off the edge of the world, and that's good. 4, 5, 6, 7, 6, 5, 4. Very good. So that is it for the HexWorld coding demo. I hope you guys enjoyed, and let me know if you have any questions. All right, thanks, y'all.